Hey guys, welcome to my second video in the alkene reaction series. Today we'll be going over hydration reactions, which is the electrophilic addition of water to an alkene. Here are a few definitions for you to know. What is an electrophile? It's an atom that is electron poor. It is an electron pair receptor and it carries a positive charge. It can also carry a partially positive charge as well. A nucleophile. It'll be the opposite of an electrophile, whereas it is an atom that is electron rich. It is an electron pair donor and it carries a lone pair or a pi bond. And it doesn't always carry a negative charge. As we'll see with these reactions, your nucleophile will be the alkene. It could carry a partially negative charge as well. Carbocations. Those are your ions with positively charged carbon atoms. An acid catalyzed reaction, that's a reaction that is fueled by an acid. Polar protic solvent, a solvent that can hydrogen bond and solvate cations and anions. So in this reaction, you are undergoing an addition reaction to add water. But of course, water can't act alone. It's a neutral molecule. So what does it do? It uses a polar protic solvent, like sulfuric acid, to protonate the alkene. But how does it do it? Basically, sulfuric acid and water undergo a reaction to form your hydronium ion. That is going to be your electrophile in this reaction. As with all alkene reactions, they only react with electrophiles. If there's no electrophile present, no reaction will occur. Let's get the general idea of this mechanism down. 3 bonds are broken. Your hydrogen to oxygen bond in your hydronium ion, your pi bond in the alkene, and your hydrogen to oxygen bond in water. 2 sigma bonds replace the pi bond. That's going to be your carbon to hydrogen bond and your carbon to alcohol bond. Thermodynamically, there are exothermic reactions, which means that the 3 bonds that are formed release more energy than the energy needed to break the pi bond. Let's talk about the general reaction. So here we have a symmetrical alkene. It's reacting with water and sulfuric acid to add on an alcohol group and a hydrogen atom. Specifically, how does the hydronium ion form? Let's take a look at sulfuric acid. Sulfuric acid is a strong acid, therefore it undergoes a dissociation reaction. It forms a hydrogen ion and a bisulfate ion. Your bisulfate ion will be a spectator ion, meaning that it won't have an effect in the reaction, so you can just ignore that. Looking at the oxygen in water, it has a partial negative charge, therefore it will form a bond with this hydrogen ion and form your hydronium ion. Now let's get to the mechanism. Say for instance we have this cyclohexene. The double bond will want to protonate the hydrogen atom from the hydronium ion and it'll expel the electrons back into oxygen, forming a secondary carbocation. Now you have the oxygen and water wanting to form a bond with that carbocation, leading to oxygen having a positive charge. So this is highly unstable. What's going to happen next is that water is going to want to protonate a hydrogen. It'll expel the electrons back into oxygen and leave you with an alcohol group. Notice that your hydronium ion is regenerated at the end. Therefore, the hydronium ion is considered a catalyst. Remember that a catalyst is meant to speed up reactions, therefore it's not being consumed in the reaction and will be there at the end. So just make sure that you notice that when you go through your mechanism. This is why it's an acid catalyzed reaction. What if you have an unsymmetrical alkene? Markovnikov's rule stands. Only the most stable product will form. So let's take a look at this example. This unsymmetrical alkene undergoes a reaction with water and sulfuric acid to form one of these two intermediates. You either have a primary carbocation or you have a tertiary carbocation. Which one do you think will form? Pause the video and see if you can figure it out. The answer is this one. Your tertiary carbocation will form. Why? Because it is much more stable and it takes up less energy to add your alcohol group to the tertiary carbocation than it takes to add to your primary. This will lead you to this product, where you have your alcohol group bonded to your tertiary carbon. Keep in mind that wherever you have carbocation intermediates, you can have carbocation rearrangements occurring. So let's say, for instance, you have this dimethylcyclohexene here, and you react it with water and sulfuric acid. Naturally, you would form a secondary carbocation, but look at the carbon next to it. Can't you form a tertiary carbocation if you were just to move over the methyl group? That's exactly what happens in this reaction. The methyl group moves over and it forms a tertiary carbocation where it is much more stable and your alcohol group will end up forming. This is called a methyl shift, specifically a 1,2 methyl shift, since it's going from carbon 1 to carbon 2. You can also have hydride shifts occur. This is just the switch of hydrogen onto another carbon atom. Let's talk about the stereochemistry behind this reaction. You could have a front or backside attack with your hydrogen and your alcohol group. If it attacks on the same side, you'll have a syn addition. So your hydrogen does a front side attack and your alcohol group also does a front side attack. If it's on opposite sides, you'll have an anti-addition. In this instance, your hydrogen atom attacks from the front, while your alcohol group attacked from the back. These are your enantiomers. Notice how your groups aren't on the same sides in both of these molecules. To sum this section up, try out this example. Pause the video. So in this problem, the alkene bond takes away the hydrogen, expels the electrons back into oxygen, and forms a tertiary carbocation. The oxygen in the water molecule creates a bond with that carbocation, and another water molecule comes in and grabs the hydrogen atom, expelling the electrons back into oxygen, just so that you can get rid of that positive charge that it has. The resultant product will have an alcohol group bonded to a tertiary carbon and your hydrogen bonded to your primary carbon. Now, try out this example. Keep in mind that you're starting off with a 6-membered ring and ending up with a 7-membered ring. There is ring expansion that occurs in this problem. Okay, really somewhat long problem. So the double bond is going to react with your hydronium ion as usual. It'll take away the hydrogen atom, expel your electrons back into oxygen, and form a secondary carbocation. Now, you could also make a tertiary carbocation here, can't you? That's exactly what's going to happen. But now you're going to have to do a ring expansion in order to make that happen. So this carbon atom goes and attaches itself to this carbon, expanding into a 7-membered ring. The oxygen in your water molecule will attach itself to the tertiary carbocation, proceeding with the normal reaction, where now you have another water molecule that takes away your hydrogen expels the electrons back into oxygen in order to take away the positive charge. And it leaves you with an alcohol group now bonded to the tertiary carbon. Alright guys, so that is it for my video. If you have any questions, leave it in the comments below. Don't forget to subscribe and give me a thumbs up if this helped you.